Good evening, everyone. Welcome to York Observatory's TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live tonight from the Alan I. Carswell Observatory, located at York University in Toronto, Ontario, Canada. TeleTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. For any questions or comments you have about our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. If you, like many of us, are having trouble remembering what day it is, make sure to pick up our calendar at the York University bookstore as well, or by going to our website observatory.info.yorku.ca and clicking store. You can connect with us on Twitter and Instagram with the handle at York Observatory and Facebook at Alan I. Carswell Observatory. So let's go ahead and get started with our amazing show tonight. So our amazing, I suppose I should say. We have a amazing crew lined up for you tonight. We have all kinds of things going on. I am Dr. Hyde, and I will be here tonight to answer any questions that you might have, or any questions that our hosts might have. I am joined today with Professor Paul Delaney, and our hosts this evening are Austin, Amin, Anita, Laur, Matt, and we also have telescope operators Richard and Sorena standing by at the 1 meter in case the weather clears. Tonight we've got a great AMA lined up, so get ready to ask us anything. Now we're just getting started here, of course, getting ready for all kinds of fun stuff. So before we get started with our official show, and depending on how it goes with the telescope and the weather, I figured let's go ahead and remind everybody just what's up tonight. So from Toronto, we can see actually Mars, we can see Andromeda, and we can see Uranus. So I'll just fix that live. um, we have all kinds of great things. We've got in the southwest Mars, very, very close to the beautiful Pleiades, as well as the constellations Orion and the Andromeda Galaxy. So keep an eye out for the Orion Nebula if you've got clear skies where you are. And located under Orion's belt, as well as the Hyades star cluster, there's a bright red star that acts as the bullseye in Taurus. The Pleiades are particularly bright and lovely tonight next to the red planet Mars, so you get a good color combination of red and blue. Mars and the Pleiades are very close together today's sky. So with the constellation Cassiopeia and the Andromeda Galaxy are also out there looking absolutely spectacular tonight. Visible a bit lower in the western sky, and there is a double cluster in Perseus, which you might be able to make out. So try to spot these constellations if you get a chance to stargaze. A pair of binoculars or a small telescope are also excellent options to see some of the deeper space objects, such as clusters or nebulae. So let us know what you can see in the YouTube chat. So I understand that we might be able to pull out just a few stars of the Pleiades. It is a little bit cloudy, but let's go ahead and give it a try. Let's see if we can connect to the 1 meter telescope and get a. Oh, there we go. That is a bit of clouds that we have on the. That is quite a bit of clouds. Professor Delaney, why don't you hop in and ask me anything you want to about these stars?
How do we clear cloud? That is the question that astronomers have been asking for millennia. Have you got an answer? How do we clear clouds?
Well, you just have to go up into space, and this is the answer to actually most of astronomers' questions about the weather.
You've got to be patient is what it amounts to. The Pleiades, as you say, is a beautiful cluster. It's actually one of those wonderful objects with binoculars. You actually don't need a 1 meter telescope to have a good view of the Pleiades over there in the constellation of Taurus. But, the telescope does bring out many, many more stars. It was always one of my favorite winter objects. I know we're approaching spring, but having the Pleiades high in the sky along with Orion always spoke to me about midwinter here in Canada.
I have to agree. I always have found the Pleiades to be just a really, really fun constellation, not just because of their beautiful blue color, but also they have such an amazing history for humanity, with the name, of course, the Seven Sisters, when we can only see six, and the
I can't
legend
even
going.
see that many personally, but anyway.
Well, I'm counting. What is that? Three that we can see through the clouds at the moment.
It's very true. Very true.
If I squint, I can see just about three. So the Pleiades is I suppose, in the spirit of Ask Me Anything, we should make sure to tell folks exactly what this is. This is an open cluster, and the blue color comes from the large number of bright blue young stars that are in the constellation of Pleiades. And just as a little shout out, Professor Delaney, you do have someone saying hello to you specifically. So Michelle is saying hi over in chat.
Hi there, Michelle. I haven't got that chat up at this point in time. I'm technologically challenged. If I have too many things open, you're going to lose me. So I'll let you relay those comments, Elena.
Yeah, we will be passing as many questions as we can throughout tonight. And now let's just see. We've got a bit of light coming through. Our telescope operators are obviously trying to adjust the screen for us, but I think they've done about all they can do on the Pleiades. Now this is Richard and Sorena over at the 1 meter telescope live right now.
While we're chatting, I'm going to make a suggestion. The Orion Nebula should be high in the sky as well at the moment. That might be an object for them to cut their teeth on, shall we say?
Absolutely. That would be absolutely wonderful. Let's see if we can get the next object up here.
Yeah.
And here it looks like they're going to
M42.
M42. Yes, the Messier catalog, one of the most useful for people who want to find fun objects in a hurry.
Absolutely. I always felt sorry for Charles Messier. I mean, he was such a dedicated observer looking for comets, and he kept tripping over these non-stellar objects, globular clusters, open clusters, nebulae. And that's, of course, how we got our Messier catalog of, is it 109 or 110? I never do remember. All of those wonderful objects that he cataloged there at the latter part of the 18th century. And then he went on to find, I think, about a dozen comets in total. So he had a very, very successful career as an astronomer. Of course, his skies were great. No such thing as light pollution back then. Didn't get distracted by sort of YouTube or other computers.
Well, now we can use our computers to show live images, so it's not all bad.
Oh, absolutely not.
All right, it looks like we're just adjusting a few settings over at the 1 meter telescope. The screen you see hopping in and out, that is actually the navigation screen. So if you haven't seen our live imaging before, that's the navigation screen on campus that they're running the telescope, and that's how they're moving the telescope in the sky. So they use that to select the object, and then the image comes through to the eyepiece cam where we can see it here. So I'm not seeing a lot yet. I'm guessing they're still setting up. Probably the dome, maybe.
Well, that could also be an issue between a bit of cloud and a little bit of dome and a few settings here and there. It's always a challenge to bring objects in real time.
Yes, I'll just take a minute to hope that the auto exposure time is on. So let's just see if we can get that adjusted and bring out a bit more of exposure coming through.
Of course, Orion is right on the meridian at this time of night, so it's prime position, so as to speak. The winter constellations, as they heading over into spring, there of Orion and Gemini, Auriga, very beautiful collection of stars. You could see them with the naked eye, even in bright city skies like Toronto. Binoculars bring them out very well. Lots of Messier objects in Auriga, M36, 37, 38, all nice open clusters. M35 in Gemini. It's just a rich playground to wander around.
Absolutely. Let's see if we can get the gain turned up a bit on this one. If you turn up the gain and the overall exposure time, we might be able to get the image to come through. I think the gain of about 5 was what I used last time we were trying to pull this particular image through the eyepiece cam. It is showing up a little bit better, and we just need to crank the exposure time all the way up to maximum on both sliders and get the gain up to about, I think, probably, maybe even 7 or 8.
It also looks as if the heart of the nebula might be a little bit off. Yes, they've read my mind. Yep, just a little bit off to the right. Yeah, there's the trapezium. So the stars are coming through the cloud. We're just not pulling up very much of the nebulosity yet.
Yeah, I think once we've got a little bit more gain on there, we'll start to get it. I'm getting an idea of the nebulosity sort of peeking through here. We do have a bit of clouds on campus, so that's not obviously helping us very much.
But you can actually see the trapezium rather well when when it's very clear. The trapezium tends to bleed together, and you don't see the 4 stars very well. But at the moment, you can actually see them. So that is certainly an indication that there is a touch too much cloud for our likings there.
What do you say we try something a little more compact? How about the beehive cluster? That should be up somewhere.
It's going to be 2 to 3 hours over. Absolutely, over there in Cancer. That would be worth giving a whirl.
So beehive, maybe this will be an Ask Me Anything. What's the Messier number for the beehive cluster?
Ooh. Am I allowed to guess?
Yes, absolutely. Absolutely.
44.
And the keen-eyed amongst you on YouTube will have seen that come up when they went over to search for it on the control computer.
Is one aspect of the plane wave 1 meter. It really does set very well. Even though we've got clouds, the telescope is able to set on a dime. The fact that we're not seeing anything is not the telescope's fault. It's purely our sky conditions.
Well, since we've got a few minutes while we're getting started going to the beehive cluster, there is actually a related question in chat, which is a really good one. Something that we get kind of often here at the observatory, but for a beginner, what kind of telescope would be a great fit?
Oh, right.
Yes, the eternal question.
Yeah.
Do you need a telescope, or would binoculars do?
Always a good question to ask because, let's face it, when you're starting out in astronomy, you're perhaps not sure that you're going to stay with astronomy. I mean, we all hope that you do, but, if you buy an expensive telescope and then, let's say, a month or 2 from now, you decide that astronomy is not your thing, it's pretty hard to use that telescope for anything else other than astronomy. Whereas binoculars, you can take them to the Blue Jays game, you can take them to the Raptors game, you can go out and do bird watching, and it's a very versatile instrument by itself, a pair of binoculars. Good binoculars on a tripod, often is my recommendation as your first optical aid. But that said, if you do want to buy a telescope, you're keen, you're certain that astronomy is where it's going to be for you, you plan to spend many nights out getting cold and so on. Reflecting telescopes, generally speaking, 4.5 inch to 6 inches, which I know is sort of like, somewhere in the vicinity of 15 centimeters to 20 centimeters. That type of diameter mirror is a nice size. Newtonian telescopes are somewhat less expensive. Dobsonians are less expensive. To me, however, you need to buy a telescope that has the ability to track the sky. That will save you endless measures of frustration. It will cost you a little bit more, but a nice, as I say, 15 centimeter reflecting telescope with a sidereal drive, nice sturdy mount. To me, that's one of the best introductory telescopes that you can buy.
And I'll just go ahead and make a small shout out to one of our very first teletubes ever. Our current coordinator, Quentin, did a wonderful video of how to make a planisphere, which is actually one of my favorite optical aids. It's not a telescope, it's not binoculars, it's just paper. And it's a chart that you can hold up in your hands and look where the stars are, move it around for different dates. They're really, really fun, very easy to make. And our coordinator, Quentin, did a great job explaining it on one of our earlier episodes. So I won't go into it here, but it's actually one of the first things about astronomy that I really ended up falling in love with. So we do have a bit too many clouds at the moment. So what I'm going to do is we're going to navigate away back from the 1 meter. The clouds are moving in, but we will come back if it clears again. So what I'm going to do is to just grab our presentation here, back over to one of our set formats, and we'll go back to the 1 meter telescope if it clears, and we'll try to see if we can get to maybe the Beehive Nebula or another bright object. So if they're able to get another bright object in the screen, we will let you know. In the meantime, we have all kinds of fabulous questions loaded up, and our hosts have prepared quite a set for us. Amin, you are up first. So actually, before we go to your question, I just want to go ahead and load up your slide. There we go. Oh, and okay, so Amin, I believe you have a question for both of us. One at a time, please.
Yeah, and it's actually two parts. So my question is, why is the Big Bang expected to have created equal amounts of matter and antimatter? And also, how can we tell apart matter and antimatter in the distant universe?
Okay, what happened to those easy questions? I mean, really?
Oh, no, you trust me, you got the easy question.
Okay. Do you want to start?
I can definitely start. It's the matter and antimatter. Why it's expected to have created the universe that it has created is probably a question for cosmologists far smarter than myself. So I'm going to leave that alone. But I will say that when we're looking at the early universe, the distant universe, there's a tremendous amount we can't see. So telling apart matter and antimatter is something that we're going to have to tackle at some point, but we still can't tell apart necessarily regular matter and baryonic matter and dark matter. We don't know what the dark energy is doing. So it's incredible. I just like to call out with this question, it's incredibly difficult to tell things about the early universe because it is at such incredible distances to us. As you've shown here with your diagram, we had a period of inflation. So we can tell things, of course, about the cosmic microwave background radiation, and look at sort of early fluctuations in the early universe and how matter and antimatter were thought to have nearly but not quite annihilated. But it is in large part still very mysterious.
There's certainly no reason that I'm aware of that would suggest that we would have to have a matter-dominated universe, that matter and antimatter should have been made in equal amounts back at time just after t equals 0. The fact that, of course, when matter and antimatter do get together, they annihilate, there's an energy signature and so on. Obviously, the fact that you and I are having this conversation means that matter did win out. But the amount of dominance that matter had over antimatter back nearly 14 billion years ago, by all accounts, was minuscule. Why it was that we ended up with the matter dominated is up for conjecture. And certainly, as Elena indicated, cosmologists far better than she or me have argued this point for long periods of time, trying to ascertain the reasons why. I won't say it's shrouded in mystery, but it is so hard to tease out those levels of detail from such a long period ago. And so we're left with our theoretical colleagues trying to make sense of the data, the observations that we do have, and the obvious statement that we live in a matter-dominated universe, given the fact that they should have been made in essentially equal amounts back at time t equals 0. So it is one of those ongoing questions, but there are a number of theories out there. But in essence, we ended up with just a slight, and I do mean slight, minuscule imbalance. And that imbalance, if you will, ran away with the matter domination.
Yeah, as I recall, there is some discussion, of course, about early fluctuations in the universe possibly helping, but we probably shouldn't go in too much detail to that. We should probably get to the next question from Amin here, as I know that there are a good stack of questions waiting for us.
Okay, I hope this one will be a bit easier. So it's just simply, how does Hawking radiation work?
Easy question, huh? Hawking radiation. Well, we should probably say a little something about black holes.
Yeah. Exactly. These are concentrations of matter that are so dense, so compacted, that the escape velocity from these objects is beyond the speed of light. We've probably all heard of the event horizon. And basically, what that means is it's a distance from the center, the geometric center of the concentration of matter. And at that distance, at the event horizon, if you transgress the event horizon, then you are trapped by the gravitational field of the black hole, never to escape. And if you pass just outside the event horizon, well, it doesn't matter whether or not your matter or energy, you're going to be disturbed. Your pathway is going to be altered by the gravitational pull of the black hole. So you don't want to get too close to a black hole, is the bottom line to that.
Yeah, especially actually the intermediate black holes, the extremely large black holes with very large diameters. One of the interesting things is you could actually walk up fairly close to it, all gravity aside. But it is an absolutely amazing object. It's been theoretically predicted. Of course, we have the famous predictions of Chandrasekhar and all kinds of history behind these mysterious objects. But oh my gosh, we can't forget, of course, the recent imaging of the region around a black hole by, I believe it was called the Event Horizon Camera or Event Horizon Mission.
Event Horizon Telescope, actually, which was, of course, a consortium of telescopes all across the planet. We turned the planet into a telescope.
Absolutely amazing. And the Hawking radiation is a very strange idea because we've heard of black holes. They're in our imagination. It's this unimaginably dense region where everything goes in and nothing comes out. But Hawking radiation actually does kind of come out. So what is Hawking radiation? It's kind of the only thing that can come out of a black hole. So Hawking radiation is basically released by black holes due to quantum effects. And this is where, again, I will refer to quantum physicists much more proficient than myself. But it allows for a black hole to release something. Although I don't know what the observational evidence for this is. It would be very, very, very faint.
I don't think we've actually made an observational confirmation of it, but theoretically, there is this radiation which does emit. And as I understand it, as you said, it's a quantum effect, but it's a pair production process, which basically has one part of the pair disappearing into the black hole, and then for conservation of momentum, the other goes in the opposite direction, which is back out into our universe. And that is the weak signature associated with the Hawking radiation. It's too weak for us to see at these sorts of distances, but it is. I'm certainly not going to argue with Stephen Hawking. If he says it's there based upon his calculations, his theories, I'd like to put money on it that it is present. But you've got to get a whole lot closer to be able to detect it.
Absolutely, and it is worth noting that with these radiations, it has been predicted. I recall that the radiation will be stronger, or the radiation will be hotter for lower mass black holes. So it's the inverse. So the radiation temperature is inversely proportional to the black hole's mass. So if you want to get a detectable signature out of this, you need to look to micro black holes. And because they haven't found they haven't found a signature yet. It actually kind of limits the amount of micro black holes that are floating around that we could detect. So if you're worried about getting hit by a micro black hole, maybe don't worry so much.
I was going to say that's probably a good thing that we haven't found too many of them, because that when they were first being postulated, I think everybody was thinking, "Oh my gosh, when is one going to plow through the Earth or plow through me if they're as common as the thought might have been?" So I'm glad we haven't found too many micro black holes.
Ditto. All right, so we got a few more questions to go through. Austin, you're up next. You've got, I think, 2 questions.
Yes, I do. So the first one is a two-parter. And Dr. Hyde, Richard Feynman refers to the double slit experiment as a phenomenon which is absolutely impossible to explain in any classical way, and that in reality, it contains the only mystery. Can you explain the double slit experiment? What's so odd about the experiment?
Well, I wouldn't say it's the only mystery. There's an awful lot that's very mysterious about science, and I think the more you study it, the more mysterious it gets, or at least the more mysterious it gets to me. But the double slit experiment is very interesting. So, without going again too far down the rabbit hole, with the double slit experiment, what you see is light going through 2 different little entrances and combining into a pattern. And this is interesting because if you use certain types of light, they have sort of designated frequencies or designated wavelengths. So if you use, for example, laser light, you can shine your light through and you know exactly what that light's doing. And when it comes through, its behavior as it comes through these slits, it combines into a wave-like pattern. So this image you have here is quite good because it's showing what the light wave would do as it goes through this little screen that's set up. And it combines into this wave-like pattern. Light also has a particle behavior. Light can be expressed as a photon, which is a particle. And so if you have a particle going through one slit or a particle going through the other slit, how is it also a wave? And so how is light a wave and a particle is the mystery. But light is a wave and it is a particle, and it was actually 2 different Nobel Prizes that established these both as true. And so this wave theory of light is sometimes referred to as a Young's experiment or Young's double slit, because it was in the 1800s that this wave behavior was found. People were like, yes, it's definitely a wave. It has a lot of uses for optics and optical equipment and all kinds of great things.
I remember when I first started learning about light at sort of high school and then into university, it always used to give me a headache to try and think of light as carrying both wave-like and particle-like properties, because we can devise experiments that clearly demonstrate the wave-like and the particle-like properties. My recommendation to people is don't try and pigeonhole light as a wave and a particle. Rather, light possesses these properties and manifests itself, as we can see in this particular experiment. But you shouldn't think of wave as, you shouldn't think of light as a traveling wave. It is a disturbance that has wave and particle-like properties, but the old analogy of saying, light looks a little bit like a water wave rippling across a tank and so on and so on, I think that probably sets you down the wrong pathway. Think of light as this disturbance that is able to manifest itself with wave-like and particle-like properties, but don't think of it as a water wave. Think of it as light, and it is unique to itself, and it is able to show you these differing properties.
Exactly. And it is worth mentioning as well that when you get into the wave behavior of light, light is a wave. It's an electromagnetic wave.
Mm-hmm.
And of course, it comes from the electric and the magnetic forces involved. And it does get quite interesting as you zoom into it. It's a very, very different from things at larger scales, the sort of the mechanical world that we're used to. All right. So Austin, you've got another question here.
Yes, I do. Now, Dr. Delaney, have you ever been curious about the beginning of the universe? What are your thoughts on the Big Bang model and cyclic versus inflationary models?
Well, I've sort of grown up with variations on a theme, shall we say. I mean, the Big Bang theory came into existence in and around the 1940s. And while I'm not quite that old yet, nonetheless, the details associated with it were in great flux all through the 70s, the 80s. In fact, I remember very clearly learning about the possibility that the universe would be sufficiently massive that its expansion would stop and then it would begin to collapse back to the big crunch and so on. So that we no longer believe is the case. The universe is expanding at an accelerating rate. So there have been lots of details that have changed because, of course, we've gotten better at collecting data, more information from the universe as a whole. I think everybody has thought about time t equals 0. I remember writing even, compositions at high school about spaceships that would go off looking for the edge of the universe because I didn't know very much about the universe at that point in time. I think all of us have thought about what happened back there and at time t equals 0. And those first few seconds when you sort of break it down and the forces were distilling out and we were going from sort of the primordial soup of just energy, and then we were able to eke out a few subatomic particles, and then a few minutes later we were getting down to creating particles, and then a little while. It's really wild stuff. I mean, it's just mind-boggling. I'm an observational astronomer. I like being able to put my eye to the eyepiece of a telescope and seeing things. When I think about the Big Bang, to coin a phrase that I used earlier, it makes my head hurt because it is so far back in time in a universe that it was so alien to what exists today. But am I curious about it? Absolutely. Time t equals 0 is a very special moment in time. And to think that everything around us today arose out of those first moments in history, to me is just mind-boggling. And to try and put that into context in the form of inflation and then the radiation domination of the universe and then dripping over into the matter domination, all in the space of 350, 400,000 years. I mean, it just is an amazing period of time. And to try and pin down all the details, well, it's job security for my theoretical colleagues. They're going to be hard pressed to pin down all the details despite their very best of efforts.
Indeed. All right. So we should probably move on a little bit. So we've got a question from Laur. Laur, are you ready to go with your first question?
Yes. It's actually directed to you, Dr. Hyde. Is our galaxy, the Milky Way, expanding at all, or will it collapse at some point?
That is a wonderful question. So, of course, I just swallowed my tea slightly wrong, so I'll get a little help from Paul on this one.
Our galaxy really doesn't change significantly as a function of time, courtesy of things like the expansion of the universe. We do move through the intergalactic medium and we do pick up a little bit of gas and we strip away gas from other nearby dwarf galaxies. And in fact, the Milky Way acts a little greedily on occasions and absorbs other smaller dwarf galaxies. So in that sense, the galactic population does actually increase ever so little bit with time. It's going to increase rather dramatically about 4 or 5 billion years from now when we merge with the Andromeda galaxy. But the galaxy as a whole, if you take a snapshot today and then you fast forward the better part of 1 billion years, there really will be precious little difference in the appearance. The spiral arms may have moved in their configuration a little bit. Some stars will have disappeared from your map. Others will have replaced it. But in large measure, the Milky Way galaxy has not undergone significant change for several billion years. When our central black hole and its accretion disk shut down, I don't exactly know what date that was. So the galaxy would have looked fairly different back then with a really bright central nucleus. But thereafter, as I say, the galaxy doesn't change much with time. But wait 4 to 5 billion years and the presence of Andromeda, then things will get a little exciting.
Yeah, over very, very long time scales, things do change amazingly. And it's worth noting that if you go the other direction in time to much earlier epochs, it's thought that our galaxy, the Milky Way, used to be made up of, well, lots and lots of smaller galaxies. There was no Milky Way. There was lots of small little primordial mini galaxies floating around and that eventually sort of came together under some sort of hierarchical Pac-Man like one eating the other kind of behavior. So in that sense, it's not like you get expansion or collapse really when you're dealing at galaxy scales. You sort of get things that are absorbed into other things and that combine and come together or get pulled apart. So it's galaxies are very, very graceful creatures, I think.
And big.
and and big, exactly. Laura, you have another question?
Yes, this one goes out to Dr. Delaney. What is your favorite thing in the universe that you can see?
Oh gosh. Wow, that's a really interesting question. There are lots of things that I really like to see. To be perfectly honest, one of the neatest sights is the Large Magellanic Cloud. It's not visible here in the Northern Hemisphere. You have to be in the Southern Hemisphere. So I'm showing my bias in this regard. I am an Australian and a Canadian, but the Australian sky, the Milky Way galaxy spreads out overhead there. It's much higher in our local sky. But beside the Milky Way is the large and the small, but the Large Magellanic Cloud is this really, it's a very intricate object in the sky. It really does at a first glance look like a cloud. And you go, oh, it's cloudy. Damn, I don't want to be observing it. But the cloud doesn't move with respect to everything else. And then you realize, oh my gosh, that's the LMC, the Large Magellanic Cloud. It's got, several million, I think about 20 million stars, roughly speaking, but it's clearly visible to the naked eye, which is really, really amazing. We've got Andromeda up here, but Andromeda at the best of times just looks like a point source to the naked eye. You get it in the telescope and it looks a whole lot better. But the LMC is so clearly evident to the naked eye, and it's a collection of stars that's outside our galaxy. That's the point here. It's not a collection of stars in our galaxy. It's actually an extragalactic object that is so clearly two-dimensional to the naked eye. It really is a nice sight. I mean, there's lots of wonderful things. I like looking at MSCA Object 42, the Andromeda, the Orion Nebula, M31, the Andromeda Galaxy is really nice. I like bright double stars like Beta Cygni and so on. The Ring Nebula. There's lots of wonderful objects, but for the one that perhaps is my most favorite one and what I always look for when I go back to Australia, the Large Magellanic Cloud.
Wonderful. Yeah, I have to say I agree. The Large Magellanic Cloud and the Small Magellanic Cloud were really eerie the first time I saw them, because you look at it, but the thing that people don't always remember is that astronomers have, I mean, usually, at least most of the astronomers I've always met seem to have really, really good imaginations. And so when we look at this object, we're not just picturing it as we see it with our eyes. We're trying to put this to the facts that we know. Like, for example, that this is another galaxy. It's outside of our galaxy. It's mind-bogglingly far away. It's a whole nother system, and you can really sit there and imagine it. And I think, if you're picking a favorite thing to look at, it's going to be the ones that really sparks your imagination. So of course I'll go ahead and say Mars again, because
it's a nice object too. There's no question.
All right. So there's one more really fun question here from Laur. So we'll have to speed up a little bit, but Laur, do you want to go ahead with your third question? Oh, if you're able to. No worries. You're still with us?
Yes, now I am. This one goes out to both professors. What are your opinions about other life on planets, microorganisms versus aliens?
You go first.
I hope they exist. I have a lot of hope and thoughts about what they might look like, I'm very optimistic, but I factually, obviously we don't know anybody, but microorganisms versus aliens, I would say I have a lot more hope for microorganisms than I do for ETs.
I agree. I think the amount of real estate which we are now convinced exists inside the Milky Way galaxy, and of course, by extension, all other galaxies, it seems to me to be a highly likely scenario that microbial life will exist elsewhere. That life being as tenacious as it is, as what we have seen here on Earth, is going to have formed on other planets, on exoplanets somewhere in our galaxy. Whether or not aliens exist, I hope they do. I am cautiously optimistic, but the necessity for the right habitable conditions for macroscopic life to evolve, an ET to evolve, even for humans, birds, and so on to evolve, that's certainly a lot more challenging than microbial life. Microbial life, it really doesn't care about the environment much. It's going to survive almost anything. Extremophiles are a great example of the tenacity associated with life. Aliens, I mean, imagine us trying to go and live on Mars without a spacesuit. Ain't going to happen very easily. So, alien life, I'm hopeful, but not as confident as microbial life.
Indeed. All right. So Anita, you're up next with some questions.
Yes, thank you. So, Dr. Hyde, we know that every galaxy forms within a dark matter halo. In other words, the formation and growth of the galaxies is connected to the growth of the halos in which the galaxies are formed. However, astronomers have discovered a galaxy that appears to lack the dark matter halo. Since your research is mostly focused on galaxy formation, how would you explain the lack of dark halo in this discovered galaxy?
Yeah, so I think I know the one you're discussing here. This is an interesting object that seemed not to have a dark matter halo. I believe some follow-up observations have sort of cast some doubt on that initial no dark matter halo assessment, shall we say? But it is worth noting that this galaxy, this is one of the things that happens when you try to observe distant galaxies. It gets very, very, very hard to say exactly what's happening with the matter and the dark matter in very distant galaxies because of their extreme distance. We have trouble even seeing stars that are far away within our own galaxy, and this is a whole nother galaxy. So in this case, I would say that this is probably an area to look a little closer in, and to see, how well it really stands up if there's really no dark matter halo. I would be surprised. I think that, there's been some evidence that there's something there. So what we really need are my favorite thing, which is more observations. We need lots more observations. We need more data. And I think, dark matter halos do seem to be integral to galaxy formation. In particular, if you go back early enough into the universe, one of the theories is that the original sort of, shall I say, overdensities and underdensities in dark matter actually helped the baryonic matter, the matter that we know of that made all the stars, helped it group together and helped form galaxies as we know it. So dark matter has been helpful to us, if this is true, and it would also make it a little bit less likely that there's really no dark matter in this particular galaxy. So I'll just go ahead and skip along really quickly here. Let's get to your next question.
So, Dr. Delaney, in all these years that you have been researching on the variable stars, were there any cases at which the observation did not match with the theories and expectations?
Not at a particularly significant level. We're actually looking at one star at the moment by the name of B.E. Lin, and it really looks as if its rate of change of period with time has changed quite dramatically. In fact, it doesn't look like it's changing at all at the moment. And that's perhaps the most significant unexpected observation that we have made. The stars that we've been monitoring, like most variable stars, are fairly well behaved. Remember that stars evolve on timescales that are, generally speaking, measured in millions to billions of years. And so to find things that are unusual on timescales of hours, days, years even, is a little unexpected, a little unusual, at least for variable stars, intrinsic variable stars. Extrinsic variable stars, things like exoplanets orbiting around their parent stars and so on, their things can go off the rails a little more quickly, but variable stars tend to be fairly well behaved. But as I said, one of the stars that we are monitoring at the moment, BE Lin, looks as if it has stopped its pulsation rate change. And if that is in fact the case, and now I'm going to sort of echo what Elena just said, more data is essential to determine whether or not this has really happened. But if it has, that will perhaps be one of the most significant things that we've actually found here at the observatory in the last 25 years.
Indeed. We love to find it when things don't match up because that always makes it interesting.
But you worry because you look at your data and go, what did we do wrong?
Well, and that's why, as has been mentioned before, any kind of extraordinary claim needs extraordinary evidence and extraordinary data. So you'll always find whenever somebody says they've discovered something, everyone will want to point their telescopes up there and see if they can verify the discovery. Because if you've got 1,000 or 10,000 or 100,000 verifications of your result, we're all that much more likely to believe you. So let's go ahead and do a little quick call out. We have a special question that has been sent in by Mani Mehdipoor, York University's newest co-op summer student at the LNI Carswell Observatory. So I'm just going to do a quick little shout out for this first question from him. There are many space telescopes currently in functioning, but they all orbit the Earth. So all the space telescopes orbiting the Earth. Would there be a benefit in having a space telescope that orbits other astronomical bodies, such as the Moon, Mars, the Sun, or even a comet? So this is a pretty fun question.
Well, of course, Kepler was orbiting the Sun. It wasn't orbiting the Earth, and it did terrific work there for 9 years. The disadvantage in having telescopes close to the Earth is really big and the Moon is really big and they're both really bright. And so that can become a bit of a problem. You're forever dancing around the sky, making sure that the Moon or the Earth don't sneak into your field of view. But the advantage, of course, in having the telescopes close to us is you potentially can repair them, enter the space shuttle. Also, of course, your data rates are phenomenally good. So in this day and age where you're collecting lots and lots of data with all observations, being able to transmit that at high rates back to the Earth is very important. So there are a number of differing considerations. There's probably nothing that I can think of that would be advantageous, for example, to put the equivalent of the Hubble Space Telescope around Mars, other than looking at Mars itself. But having most telescopes in relatively close proximity to the Earth certainly is the standard operating procedure at the moment for astronomers. The James Webb Telescope is going to change that a little bit.
I knew you were going to say that. So actually what we're going to do is we're going to go to Matt's question, which is about the, go ahead, Matt.
Thank you. Well, my question is actually, since both of you have worked on different telescopes and know the importance of and the findings one can have with a good telescope for sure, how do you think the James Webb Telescope will change or improve what we have found so far? In other words, what other new things may we be able to find with new technologies such as this?
You want to have a shot at that one?
Yeah, well, I mean, the James Webb Telescope is arguably one of the most anticipated, and it's not just because it's been the most delayed, but its science goals are numerous and multifold. And one of the things I'll just call out is this actually relates back to our previous question, because it's not going to be in orbit around Earth per se. It's going out to one of the Lagrangian points, and I'm just not quite remembering which one.
I think it's L2.
Yeah, I think that's right as well. So once it's out there, it will not be getting a lot of the interference that, of course, Hubble has to deal with, being in, very close proximity, shall we say, to Earth. So this telescope is going to be orbiting out at a distance, and it's going to have a lot of infrared capability. So it's going to sort of extend out away from what Hubble could do, and hopefully sort of help us with a lot of the questions that we were getting earlier about the origin of the universe and all of that good stuff. So there's a lot of really, really fun things we can do with this, obviously.
And a large collecting area as well. That is the other primary characteristic of James Webb. 6 meters ish in diameter. You compare that to the Hubble telescope of 2.5, remembering that the area of the telescope goes up as the square of the radius. So we're talking about nearly 10 times more collecting area for the James Webb telescope compared to Hubble. So it's going to give us some pretty exquisite views, but as you say, Elena, in the infrared rather than in the visible.
Yeah, and one of the reasons it has been so delayed is because it's at this unusual location, and because it's so large. This is going to be 100 times more powerful than Hubble, they think, but it has to actually unfold when it gets there. So it's got this sort of transformer-like unfolding that has to happen, something like 1 million miles from Earth or so. But yes, very, very, very fun. All right, so we should move on a little bit faster, or we're going to run out of time tonight. We actually have one more question from Matt, I believe. This is probably could be a super long one, but we'll give it the shortest answer we can.
All right. Thank you. Well, other question I have, and I'm sure other people may have, probably on chat, maybe not, is that do you think that at any point in the history of humanity, we will be able to live on another planet? Just like the idea of terraforming Mars. And do you think that it is a plausible thing to think we may achieve on this century or maybe the future centuries? And what would be the reason to do that?
Oh, this is a very, very long question, but I think I'll just go. I'm just going to say yes.
Yeah. Yes, to which part, though?
Yes, and make sure to tune in next week for our special Mars episode on TeleTube, because we will actually be doing a whole Mars episode just next week about how to live on Mars.
But just, if you expand it out, not just thinking about Mars, thinking about, terraforming any planet, not only are there the technical questions associated with whether or not it can be actually achieved and on what sort of timescale. The timescale is probably going to be really a long timescale. There is the question, of course, of whether or not we have the right to do it. If the planet is barren, if you're convinced that it has no forms of life, then terraforming is perhaps an option if you've got the time and the engineering expertise. But it becomes a very different question in my mind. If there is life on that planet, even if it's rudimentary life, is that something that we really should go ahead and terraform? It's a really long and interesting discussion with many differing facets, but technologically, it's a huge challenge and it's not ever going to happen quickly.
I agree. And it is also, as you say, worth considering, if we are going off to other planets, we do have, responsibility to do it in a way that's not going to interfere with whatever might already be there. So we just have a quick Mars image coming in. The clouds have disappeared from the 1 meter telescope. This is Mars coming in live right now from the 1 meter telescope. You can see it blinking around there. That is the seeing of the atmosphere going up and down. And we're just able to see just a smidge, or maybe I'm hallucinating a bit, just a smidge of the details on the surface.
Yeah, there's a little bit there. There is a little bit there.
So the question is, would you want to live here?
Has to be underground. There's no ability to protect us from the radiation on the surface at this moment in time, not for extended periods at any rate.
Yeah, well, yeah, and it is a very harsh environment. It would be very, very extreme, and I did ask my partner, and they said that not without coffee and hot showers. So until we figure out how to do that on Mars, I'm not going to be able to move over there.
Melting the ice. At least there is ice to melt and get water. So that's a step in the right direction.
All right, so that we were able to finally bring just a few more live images back from the 1 meter telescope. So that is a really wonderful way to wrap up. Now, Anita, you had a really good ending question. So why don't you go ahead with your first end question, and we'll leave up the image of Mars for as long as we can.
Sure. So I have a general question for both of you. During the path of your studies and research, there have been probably some times that you just feel like you're frustrated and you want to give up. So my question is that what motivated you and made you continue on your path?
Well, I'm really stubborn. I don't know about Paul.
One of the things that always makes me encourages me to, quote, get out of bed and do the things the next day are students, people like you, Anita. All of you have got the eagerness that I think Elena and I had back in the day, and we want to be able to proliferate that. And so, despite the fact that there are always challenges, and I don't care what the job is that you're doing, university teaching astronomy, it's just a subset of work in general. There's always going to be frustrations, but to be able to see the light bulb go off in students' eyes because they're observing something, or they've solved a problem, they've worked hard to achieve a certain goal, that is very, very rewarding, and it delights me to see that happen sort of day in and day out, year in and year out. And that to me is what helps motivate me.
Absolutely, and it is everybody encounters obstacles of all kinds as you're traveling through, and sometimes you have to completely change the direction that you're thinking about going, and then you end up in Australia and you become an Australian, and then you do it again and you end up in Canada. And you might do it again and end up somewhere else. But there's a lot of different ways you can try to recenter yourself. But it does help a lot to have, of course, positive feedback from students, from colleagues. I have to say, at York, I've been here a year, and I will always remember my first student email that came back and said, teacher, you did something nice and it helped me. So it really actually does quite a lot for the motivation. All right, so we're just battling the clouds over on Mars at the moment. So I'm going to grab us back over to our set screen because this is actually a very nice slide that Anita has put up, and I wanted to emphasize it with this question. Don't give up. There's always another way, another path, another mode, and I have to say, one thing is, if you've got a path of studies of research, it can be quite unconventional. So I don't speak for anyone but myself, but I've taken a very, very roundabout, hopsy-turvy sort of path to get here, and it wasn't at all the normal path that you see laid out in charts and things like that.
If you're doing something that you like, it doesn't feel like work. That's the other comment perhaps to pass on here. I enjoy looking through a telescope. I enjoy teaching. I enjoy dealing with problems in and around an observatory. To me, that's not work. I feel very, very proud that I can be paid for what I almost consider to be what I enjoy doing as a hobby. So if you're doing, and it doesn't matter whether or not it's astronomy or anything else, as long as you're enjoying it, you actually never work a day in your life. It's not work.
Well, it does get quite difficult, but I would say it's the enjoyment of it is absolutely key, because that is what gives you the oomph and the strength that you need to keep going when it does get tough. And so it's a very good question. So we'll just go ahead, and I think we're running a smidge late on time, but you've got one other really good one, Anita. So let's go for that. And then I'll check chat one more time.
Thank you very much. So I just have one last question. Do you have any recommendation for students who would like to do research in physics and astronomy field?
So many recommendations. So I've written them down, all of my data science recommendations on my website, but there's a lot of recommendations I would say for people who want to do various paths. Is it always a matters like very specifically what you want to do? So not necessarily what someone else wants to do. So if if my path is like, oh, this person has done the same thing that I want to do, that can help a lot more. If you're looking at really research, so to traditional research, I'm looking for, master's programs, I'm looking for research stipends, that kind of thing, then probably you need to get into making a research CV or curriculum vitae that showcases your research and what you have done. Because if you can showcase what you've done, it's very, very believable when you bring that up to a professor or a hiring committee of some kind, and they say, well, what can you show us? And you say, well, I've done this. And that's always very, very believable. This is something that I find much more effective than high grades or anything else. If you build it and show that you can do various things, it really helps you build up your research profile. Of course, also, if you're getting into research, find out how to collaborate with people. Research is incredibly, incredibly collaborative, and I'm sure that Paul would say the same thing. It is super collaborative.
Teamwork, absolutely. And that shows up very well on a CV if you have been a part of a team, if you've, and again, it doesn't even have to be in astronomy, but to be able to exhibit teamwork, to be able to show that you have got good organization skills, that you've got good time management skills, that you can work independently. These are things that cut across all aspects of human endeavor. And if you are able to show those on your CV, if you can do some research while you're working through your courses, that really does show up well. The sorts of things that you've been doing at the observatory all go down very, very well when people are scanning your CV. You're trying to make yourself stand out. What makes you distinct from, person B, person C? Because almost any job that you apply for, or any degree that you apply for, you will not be the only one applying. And so you've got to find those mechanisms, those techniques that will show you in the best possible light, that will bring you above the noise, shall I say, to give you that 2 or 3 sigma distinction from everybody else, so that people will be able to say, yes, this person looks like they've got the skill set we need.
Exactly. And if you have things that you've done in that area that you are genuinely excited about, bring those, show them those, because when you're genuinely excited about what you do, it does come through. So that's always a good one. All right. So we've got, of course, even more questions coming in from chat. I'm not sure if we have really time to answer all of them, but we did get a question. I'll just give it a quick call out here at the end. Do you think dark matter energy is a worthy explanation for universe expansion, or do you think there's a far better theory? So this is a chat question that came through, and I think I am unqualified to answer that question. And when I am not at all amiss to say, I would have to read up and get back to you on that.
That we need to get Sean Toolan on air, or Matt
Yes.
Johnson, because they've got far greater skill sets in answering that question, because that's their area of expertise. Even Nassim would be very good in that regard. But, dark energy and dark matter have got lots going for it. The observational evidence over the last 20 years has mounted significantly. And so I certainly wouldn't want to go out on any limb and say that that wasn't the best answer based upon the data that we have today.
Any last words, folks? I think we've gotten all of our questions here.
Yeah, it's been a great evening.
It's been a wonderful evening. Thank you so much for joining us, Paul. I am going to go ahead and start wrapping up here. But we have had live images from the 1 meter telescope. We have had all kinds of questions from all kinds of folks. We have had a absolutely action-packed evening, and I think this is going to be one of our longer episodes. So everyone, you have been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the Astronomy and Astrophysics program written and presented presented by the students, faculty, alumni, and friends of York University. Thanks for joining myself, Professor Hyde, as well as Professor Paul Delaney, and all of our wonderful hosts this evening, Austin, Amin, Anita, Laur, Matt, and of course our fabulous telescope operators who brought you those live images, Richard and Sorena, and of course our newest summer co-op student, Mani Mehdipoor, who sent in their questions. And we are just really thrilled that you were able to join us for this program. So all of our programs are free, but if you'd like to make a donation, please see our website at observatory.info.yorku.ca. And you can always connect with us on Twitter with the handle at York Observatory, and of course on Instagram with the same handle as well. Check out our website for show notes, content updates, and of course contact info. Thanks for tuning in, everyone. Clear skies and have a wonderful night.